In the years that followed the French Revolution, the First Republic was formed, and during this time, the French people really failed to achieve anything. Rather, fear escalated nationwide, and a great amount of bloodshed occurred during what is known as the Reign of Terror. The end of this period left the country once again in disorder, and with the same unsolved problems which had originally motivated the revolution. During this time, France desperately needed a leader which would provide authority and confidence throughout the country. The French Revolution sought to stop one man from having absolute power, but ultimately just swapped for another. Since, just 5 years after seizing power, Napoleon assumed the imperial title, being crowned Emperor of France. It is in this Napoleonic France on the 25th of October 1811 in Bourg-Égalité that Évariste Lacroix was born. During this time in France, mathematics flourished and was held in high regards, having produced many incredible mathematicians like Cauchy, Lagrange, Legendre, Laplace, Monge, and later on, of course, Galois. Évariste was very close with his father, who was a proud Republican and a supporter of democracy and of Napoleon. In 1828, a king, Charles X, was back on the throne of France, and Republicans, like Évariste's father, were persecuted and harassed all throughout the country. That same year, at the age of 17, while studying at the Lycée Louis-le-Grand, Évariste abandoned all of his other studies in favor of math, and published his first academic paper on continued fractions. Later on, he turned his incredible and adventurous mind to the unsolvability of the quintic, and whether we can determine if any given equation of degree 5th or higher is solvable. In order to crack this solvability problem, Évariste introduced the revolutionary mathematical theory that would make him immortal: group theory. Just a few weeks before his crucial entrance exam to the prestigious École Polytechnique, his father committed suicide. This threw Évariste's life off course as he failed his exam. A few years later, at the age of 20 years old, Évariste perished in a duel. Nevertheless, fearing his own death, the night before, Galois wrote a letter containing his discoveries that would trigger a mathematical revolution. Galois was truly one of the greatest mathematicians of his time, since he solved a problem which no one had been able to figure out for about 300 years. His theory, now called Galois theory, takes problems about polynomials and turns them into problems about groups. In other words, if you have a polynomial, you can get a group out of it, which is called a Galois group. In fact, this principle, now called group theory, is a branch of abstract algebra. Group theory can be described as the mathematical language of symmetry. This is because it studies the algebraic structures known as groups. A group is a particular set of elements that when an operation is performed on two of the elements, it results in a third element of the group that meets 4 axioms. The first rule or axiom states that the set of elements must have closure. This means that there's a predefined list of actions that can never change. The second axiom states that the group must have associativity. This means that you could put parentheses wherever you want in a group operation, and it would have to be equivalent to the same operation, but with parentheses in a different place. For example, using numbers, let's say we had 3 plus 4 plus 3, and put parentheses between the first 3 and 4, or between the last 4 and 3, the result would still give 10 in both cases, since both equations are equivalent. The third axiom states that there is an identity element in the set that keeps the set unchanged. For example, with numbers, the identity property would be that if you add 0 to any element or number, this element or number will not change. Another great example of this is multiplying a certain matrix M by an identity matrix of the same size, since the final result gives the matrix M. The fourth and final axiom is the inverse, which states that there must be an inverse for every element of the set. For example, using numbers again, if we had the equation 3 plus 3, well, the inverse of that equation would be 3 minus 3. Galois realized that the structure of all these permutation groups gave him information about solutions to polynomial equations. Most of us learned in high school that if we were given an equation of second degree, we can solve it using the quadratic formula. This is also true for equations of third degree with the cubic formula, and even for equations of fourth degree with the quartic formula. As such, Galois' incredible discovery was that he proved that there was no such formula for equations of degree 5th or higher. In fact, a Rubik's cube meets the 4 axioms and therefore is considered a group. For example, the axiom on closure would be all the possible moves I can do on a Rubik's cube, since there are predefined actions that never change. Furthermore, group theory can also apply to public key cryptography and has various applications in physics. For example, Noether's theorem explained how symmetry within a system corresponds to a conservation law, and this gave mathematicians and physicists a better understanding of Einstein's theory of general relativity. Galois theory also has applications in chemistry, for example, since groups can classify certain crystal structures and symmetries within molecules.